Hey, this is Math 7, and we are on Unit 4, Lesson 14 today, again talking about percent error. This is something that came up last lesson. We were looking at measurement error, and we converted it into percentage errors. And so now we're looking at some more of the same type of thing here. So we're going to use percentages to describe other situations that involve some sort of error. Okay, so I'm going to skip to the number talk first of all and go on to the little lesson activity here for you today. There's only a couple things we're going to do, and then we're going to work through the homework situations. Okay, it's really here's what I'm finding with this lesson here. With this lesson today, reading and understanding the problem is probably the most essential thing. Being able to take time and figuring out what are they asking me to do is going to help you calculate whether I'm going to be increasing or decreasing, multiplying, dividing, whatever it might be. So we want to be careful as we read through to figure out what exactly are they looking for. So let's take a look at this first example and question. It says instructions to care for a plant say to water it with 3/4 cup of water every day. The plant has been getting 25% too much water. Okay, now 25% too much water. We have to decide, is that going to be an increase or a decrease? Well, too much sounds like a definite increase in water. How much water has the plant been getting? Well, we could say too much as an answer and be done, but that would not be precise. So let's take a look here for how we want to solve this. This plant should get the right amount, 100% of what it should get, and that's 3/4 of a cup every single day, right? It should get 100% of 3/4. That's where the 1 comes from, remember? We do 100%, we convert that into a decimal by moving it over, that's where the 1 comes from. But we know that it's getting too much, so we're going to be adding an additional amount. In our case here, it was 25% too much. So when I move this over as a decimal, I end up with 0.25 times 3/4. Okay, so at my 100%, it should be getting 100%, which is 3/4, and it's getting an additional 25%. Okay, so now we're going to group these things together. So I'm going to take my 1 plus my 0.25 and put them together, and I group my 3/4 together. Okay, and I have 1.25 times 3/4. You might be saying to yourself, well, that's kind of ugly. You have a decimal and a fraction. Yep, I do. So let me fix that up there. I'm going to just drop to the side here. 1.25 as a fraction is 1 1/4, right? It's 1 1/4. And if I want to make that into an improper, I do 4 times 1 is 4, plus 1 is 5. So that becomes 5/4. So I'm going to put that back over here. So I actually have 5/4 times 3/4, like so. So when I multiply fractions, I just go straight across. So 5 times 3 is 15, and 4 times 4 is 16. So in terms of how much water the plant is getting, it's getting 15/16 of a cup of water every time. So that is almost a whole cup. Is that a measurement that you would use? Do I have a measuring cup of that size? Probably not, but we just know it's 25% too much, which means it's getting about 1 cup more than it needs to. It gets about a cup of water every day, and it should be getting 3/4 of a cup, right? It's a little bit more. So, yeah, so that's about what we're saying there. 15/16 of a cup, and so almost one cup of water every day, which is too much. It's getting overwatered. So our process for doing that was recognizing that 25% too much was going to be an increase, which told me I'm going to add, right? I'm going to add to the initial. This is what I have, and I'm adding that point to 25% more. Let's see if we can use that same idea with the next one here, okay? Or something similar. Number 2. It says the pressure on a bicycle tire is 631 psi. That's pounds per square inch. This is 5% higher than what the manual says is the correct pressure. What is the correct pressure? Okay, now let's think about this. Okay, so what is the correct pressure? The correct pressure is actually less. I know this says 5% higher. That's true, but it's higher than the actual, right? So this amount is greater than what it should be. It's like my actual is here, okay? And I have my PSI is 63, right? It's a 5% increase. This is more than what it should be, okay? So I know I have too much here. So I'm looking for a number that's going to be less than 63 for my answer, just to kind of keep that in mind. All right, so let's take a look here. I can look at this and think about it as, when I did this before, I did my, well, let's go this way. I'm going to take my actual amount, or what I measured, sorry, the 63, and I'm going to actually divide that by the difference here, okay? So let me, I'm going to pause. Pause there. Hang on, let me come back to this. Pause. What we did before is we did 1 times our correct pressure, our actual amount, we'll call that X, okay? Now in this case here, they went up by 5%. Okay, so it went up by 5%, which is plus 0.05 times X. Okay, and that's going to give me, in this case here, we know 63 psi. So if I want to set it up the way that we did the last problem, this is how they would have gotten 63%, 63. It's 100% plus a 5% increase is what we're doing. So when I group this together, I end up with 1.05 X equals 63. So to find out what the correct pressure should be, my correct pressure is actually X, okay? So I want to divide by 1.05, divide both sides of 1.05, which is what I was writing over here, right? 63 divided by 1.05, which is then going to equal 60 pounds per square inch. Okay? So what I was doing over here was right. I wanted to come over here and show you how I got that. I did the procedure backwards. So I would just set it up the way we set the other ones. 100% of the correct plus the 5% more of the correct equaled what the pressure is going to be, 63. And then I just worked backwards to figure out, oh, it's 63 divided by 1.05. So I could have just skipped ahead and done this part there, right? If you saw that, that works fine. But if you didn't, that's okay as well. All right, so that's what gets complicated here, and I apologize for that. So sometimes my talking in my brain gets ahead of my actual working, even when I look at my notes from what I did before. So I'm just trying to make sure we're consistent in what we're doing here. So if I confused you there, sorry. That's a simple way to do it. This is the really simple way to do it, but we'll get there. Next one, number 3. The crowd at a sporting event is estimated to be 2,500 people. The exact attendance is that. Okay, what is the percent air? So when you define the difference, to find this, remember, you're going to take the actual minus the measured, or the number you did, okay, divided by the actual. So in our case here, that's 2,500 minus what we measured, 2486, divided by 2,500. So 2,500 minus 2486 is going to be equal to 14 over 2,500. 14 divided by 2,500 is equal to 0.0056, and to make that a percent air, we move the decimal place over 2 spots, and we have 0.56%. Okay, and that's the basics of the problems that you're working with today. Okay, this is kind of the key thing that you have to be able to do on probably on a unit test, is just find that difference and then divide, and you're good to go. Okay, these are the more complicated kind of questions that you might see perhaps on your end of the year test, whatever that one looks like, where you have to do a little more reading to figure out what are they looking for there. All right, I'm going to skip there. Are you ready for more? And move over to measuring in the heat. Okay, this problem here is a little bit longer and just has some more crazy numbers to deal with. It's an okay problem, but it may be a bit much for some of y'all, so it's okay. I think the basics are back on the previous page. This is taking up a step more than what some of you may be ready for, depending upon how you're doing. So let's take a look anyways. A metal measuring tape expands when the temperature goes above 50 degrees. When it goes above 50, it expands. So if it was like this length, it now becomes that length, whatever. For every degree above 50, its length increases by 0.00064%. So for every degree above 50, it increases that much. Okay? The temperature is 100 degrees Fahrenheit. Wow, so we're definitely above 50, and we're above by 50 degrees. How much longer is the 30-foot measuring tape than its correct length? Okay, so first of all, we know that it's 100 degrees And so the difference between the 100 degrees and the 50 degrees is we've increased by 50. So that 50 then is multiplied by the percent of increase. So 0.02364%. Okay. Now I can't multiply by a percent. I got to change it into a decimal. So to do a decimal, I'll move this 2 spaces that direction. So I end up with 50 times 0.00 and then 12364. By multiplying that out, what I come up with then is 0.00032. Now, what is that? So that's the increase that's going to happen because the temperature change is that much. It's increasing this much because of the temperature change, but it's going to do that for every foot of the measuring tape. So I have to take this value, okay, 0.12332. That's the increase I'm going to have because it's a 50 degree increase. That percentage, 0.00064%. But I'm going to do that for every foot. In our case here, there are 30 feet in this tape measure. So that percent increase as a decimal multiplied by the 30-foot long tape then gives me 0.0096. Okay, so my actual increase in the expanded tape measure, because it's a 30-foot tape measure, is going to be that much of an increase. Wow, that's not very significant, is it? In terms of the percent error, because it's growing by 0.0096, okay, that's our increase. We divide that amount by 30, because it's a 30-foot long tape. That's our actual, right? That's our increase, and that's our actual. And so we're going to find that that equals 0.00032. And to turn that into a percent error, we'll move that over 2 spaces and have 0.032%. Okay, a little bit of a complicated problem, just the way it's written out. You have to read it through. I had to read it a few times to say, wait, what exactly is it wanting me to do? Right? You take your 50-degree difference and multiply by the percentage of increase because of that degree difference, which gives you that amount. Okay, and that amount happens for every foot, so we multiply that by every foot, which is 30, to say that's the amount of the expansion for the tape measure there. So that's how much it's going to expand, right, total. And we do that divided by the actual, because we increased by that amount. That's the difference, and that's divided by 30, and there we are. So that's a little more complicated. I like the previous one, a little more straightforward. So percent error can be used to describe any situation where there's a correct value and an incorrect value, and we want to describe the relative difference between them. That's all we're looking at here. So when there's a correct value and an incorrect value, and we want to say, well, what's the difference between those two? That's where you might use a percent error. Okay, let's take a look at tonight's homework. So pause there, get some homework going. Let's check it. Okay, number 1, a student estimated it would take 3 hours to write a book report, but it actually took her 5 hours. What is the percent error for her estimate? So we're going to do the 5 hours minus her percent error, or for what she estimated, divided by, we want to go for her estimate. So her estimate is going to be 3. That's our bottom number there. So 5 minus 3 is 2 over 3. And 2/3 as a decimal is 0.66. So it goes on forever. As a percent, then that becomes 66%. The key thing here is that we want percent error for her estimate. The estimate is what we're looking at. We're comparing there for the estimate value. That's what tells us what number goes on the bottom in this case. Number 2, a radar gun measured the speed of a baseball at 103 miles per hour. If the baseball was actually going 102.8 miles per hour, what was the percent error in this measurement? Okay, what was the percent error in the measurement? So we have 103 was the measured minus 102.8. So our difference is going to be 0.2. That's our difference. So our difference is going to be 0.2 divided by, in this case here, in the measurement here, we would say the actual was 102.8 All right, so 102.8, so we do 0.2 divided by 102.8, and that gets us 0.00194. Move it over 2 spaces, and that becomes 0.19%. What's the difference there? All right. I'm looking at this one here. It's driving me nuts. I kind of want to go back and look at this guy here because this one is just bothering me. It's just bothering me. I know my answer key says 66%, but we kept saying that you wanted the difference. I'm going to go back up here real quick. And we would say that you would do 5 minus 3, and then the bottom number we always said was our actual. Okay, so if the actual was 5, you'd end up with 2 over 5, which as a decimal is 0.4, and so as a percent we would say is 40%. Okay, this is putting the actual on the bottom, this is putting the estimate on the bottom. Okay, I know I'm kind of jumping around here. So in terms of the percent error for the estimate would be there, the percent error of the actual would be there. The way we've been doing it, I think we would go this way, even though for whatever reason my book's saying that that's the right answer. That seems to be what we've been doing more of. Okay, we kept putting the actual down below there, and over here we did again the same thing, right? The measurement was 103, but the actual is 102. We put the actual, right, there's our actual number on the bottom. So every time you put the actual on the bottom, it works out this way. And that's what we were doing before. So I think I prefer this answer here to that one. So if we keep the same pattern going, actual will be there. I worked this one out because that's what the book was showing me how to do a little bit, but it just doesn't sit well. I think I prefer that one, but again, maybe it's just a reading thing, right? For which way do you read the problem? It's a good question. So let's see. I got to keep moving though. I'll be here for days. Let's look at the next one. It took 48 minutes to drive downtown. An app estimated it would be less than that. If the error was 20%, what was the app's estimate? Okay, so the app thought it'd be 20% less, which means this was more than the app, right? So you have the app time is less than 48, okay? It took 48. In reality, it thought it'd be less than that, so it's gonna be less than 48 for its answer there. Okay, that's what we think it's going to be. Now it said if the error was 20%, that means it's 20% error in what it was. So we're going to increase from the actual. So in our case here, it's like 100% was 48 minutes, right? And then we increased it by 20%, which is 0.20 times the 48. So 1.20 times the 48 is going to give me 40 minutes. So in terms of how long the app thought it'd be, the app thought it'd be 40 minutes long, and it was actually 48. So it thought it'd be less than that, right? It thought it'd be less than the 48, thought it'd be 40. So the error was 20%. So you're looking at 20% error in that. That's the increase in that part there. Think of it this way. Here's 40 minutes is what it said it would do. We're going to increase by 20%. We're going to increase by 20%. Well, 10% is going to be 4, right? So we're going to do plus 4 for 10%, plus another 10% is going to equal 48 for how many minutes it took there. So that is correct, and that's the way you go about getting that one there. It's just kind of funny the way these things are worded here. Number 8. A farmer estimated there were 25 gallons of water left in the tank, right? So here's a tank. It said he thought it was 25. Great. If this is an underestimate by 16%, meaning it's that and the additional 16%, right? Then how much water is actually in the tank? So that's going to be the whole 25 gallons, 100% 25, plus an additional 16% of that times 25. So we're going to have 1.16 times 25 gallons. So it's 100% plus an additional 16%, which is going to equal, in our case here, 29 gallons. All right, let's look at the review stuff here. Diego collected X kilograms of recycling. Lynn collected 2/5 more than that. So that's going to be one of those 1 times X plus 2/5 more x is what Lynn's going to collect. Okay, so 1 plus 2/5, 1 plus 2/5 times x equals y. We can do this as 1 2/5, which becomes 5, 6, 7/5, becomes 7/5 x equals y. Okay, because 5 times 1 plus 2, so that's what we say for the first one. Okay, Lynn biked x kilometers, Diego biked 3/10 less. So that is one of those 1 times x minus 3/10 x equals y. 1 minus 3/10 is going to be 7/10 x equals y. And normally we would say y equals the other, but that's okay. Diego read for x minutes, so 1 times x. Lynn read 4/7 of that. Oh, well this one's a little bit trickier. 4/7 of that. So I don't even need all this. This is 4/7 of that. Of that is the x minutes, so 4/7 of that equals Lynn's. So it's 4/7 of Lynn. So it's kind of a shortcut way there. All right. Next side, number 6. For each one, decide if it's an increase or decrease, and then determine the percentage. Okay, so y is less, so we would say that's a decrease. Now in terms of how much it decreases, we say this has 1, 2, 3, 4, 5 parts. So whenever you have 5 parts, right, 5 divided by 100, or I should do 100 divided by 5 is going to be 20. So we're going to be looking at a 20% for each space. So that's going to be a 20% decrease, right? So it's a 1/5, right? Or another way is 0.2, which is also 20%. So that's the decrease there. In this case here, we are increasing by that much. So that's an increase. And we see that initially, again, we're at counting by 20%. So 20, 30, 40, 50. So 20, 40, 60, 80, 100%. So this becomes a 20%, 20%, 20% increase times 3 is a 60% increase in the value there. Or I'm doing 3/5, which is 0.60, move it over, and that becomes 60% of an increase. Now last one, number 7, Lynn is making a window covering for a window that has a shape of a half circle on top of a square with a side lengths of 3. So it's a 3 and a 3 and a 3 and a 3. Okay, so how much fabric does she need to cover the whole thing? Here we go. Well, to cover this inside part, this is going to be a square, so 3 times 3 is 9. That's the inside part. Got it. But now I have this circle. A circle, area of a circle, is equal to pi r squared. Now I'm only doing half of that, right? Half of that. So I'm going to do 1/2 times pi times the radius squared. So this part right here is not in your teacher's answer key right now. Okay, so they might have a different answer, but this is why it's different. So 1/2 times pi. So let's put some numbers in here. 1/2 pi is 3.14. That's our estimate there. Our radius, we had the diameter is 3. Radius is half of that. So half of 3 is 1.5, and then we're going to square that value right there. Okay, so let's take a look at this. So 1.5 times 1.5 is equal to 2.25. So I have 1/2 times 3.14 times 2.25. Okay, so let's do this here. So 2.25 times 3.14 equals that, and times a half. A half is the same as what? 0.5 times 0.5 equals 3.53. And I'm just going to leave it there for that part there. So the semicircle is 3.53. I add that to the square, and I end up with 12.53. In this case here, we said it was feet, so feet squared is going to be my solution there. I'll tell you right now, the answer your teacher has is something like 16.07. If you were to add an additional 3.53, right, instead of doing half of it, if you double that up, you'd end up with that 16 amount. So the difference between the answer key and the real thing is that this is a half circle on top. That's a key difference. So there you go. Have a great day, and that's it.